Welcome back, you lovely, lovely, lovely people. In this lesson, binomial problems, our third and a half lesson, we're going to look at some more detailed binomial issues. Particularly worded type questions like this. In Joe's Cafe, what a great name, 70% of customers buy a cup of tea. In a random sample of 20, find the chance that more than 15 buy a cup of tea. Let's do a quick check first of all. Is it binomial? Hello, sir. So, are there a fixed number of trials? Yes, there are 20 of them. Can each trial be a success or a failure? Yes, either they buy it or they don't buy tea. Trials are independent. Okay, so we're going to assume here that every customer is unique, individual, and they're not affected by the choices of the person in front or behind them in the queue. And 4, the probability of success, P, is constant. Again, we find that 70% of customers buy a cup of tea. Now you might say, oh, but it depends on if it's like the morning or the evening or if it's having a meal. Doesn't matter. We're assuming with a large enough sample to assume that every person is basically the same unique, boring person. And the best ones buy tea. Now, in our distribution, we're going to define X as people who buy tea. Our N is going to be 20 customers. And our probability is 0.7. So X, we've established it can be used in the binomial distribution. There are 20 people and a 0.7 chance of success. Now, we're asked to find a chance that more than 15 buy a cup of tea. So probability that X is bigger than 15. Just do a quick check for me. Maybe pause the video and try and find in your booklet of values the values where N is 20 and P is 0.7. So hopefully you've actually paused it and had a look rather than just played along. You'd have seen that while there is a 20 section, there is no 0.7. So there's no 0.7 in the table. So what we are going to do is look at what is called the complementary random variable. Complementary random variable, which we're going to call Y. Now Y is the chance that you do not buy tea. Well, there's still 20 customers, but rather than a 0.7 chance of buying tea, there must be a 0.3 chance of not buying tea. Whatever strange people don't buy tea. So Y is again binomial 20, and this time it's 0.3, and that is in our table. But before you jump ahead, let's just check what we're looking for. And for that, we're going to use a number line. Remember, you're never too big, too clever, or too old for a beautiful number line. So this line here, it's going to be based on our X, so the chance of people buying tea. In our original question, and 20, we want to know more than 15. So that's basically 16 through 20. Those are the ones we're interested in. More than 15 buying tea. Now in our reverse case, the Y, if 20 buy tea, then 0 don't. If 19 buy tea, then 1 doesn't. 18, 2, 3, 4, 5, 6, 7, 8, etc. So the same chance of 16 buying tea is 4 or less not buying tea. So now you can jump to your tables and try and find a probability that y is less than or equal to 4, which is, you found it yet? You found it? That's right, it is 0.2375 chance 4 or less not buying tea, which is exactly the same as, that's a pink, great colour pink, x being less than 15, which is 0.2375. Oh, quick post edit. Downside of doing it by hand and doing it fast and late at night is mistakes. So obviously it says more than 15, it says more than 15 here, clearly more than 15, this should be equally more than 15, not as I wrote less than 15. Sorry. Well done if you spotted that deliberate mistake. Now we're still in Joe's Glorious Cafe, and this time we're looking at customers buying muffins. So 35% buy muffins. Find the probability that Joe sells the very first blueberry muffin, wow they look good, to the 5th customer. Now in our normal binomial situation, you think about, okay, well, you got 5 people happening, so n must be 5, and the first one is the 5th person through. So you must look at, 5 choose 1, or maybe you thought there's 20 people, I want the 5th person through. Okay, let's just think about what it takes for this scenario to occur. For exactly the 5th person to buy a muffin, we must first have, let's use M's. First person to not buy muffin, the second person not buy muffin, the third person not buy muffin, the 4th person not buy muffin, and the 5th person does buy a muffin. Alright. Now the normal binomial doesn't really care the order these are in. In fact, it calculates all the orders. So your normal binomial equations will also look at not muffin, not muffin, not muffin, muffin, not muffin, not muffin, not muffin, muffin, not muffin, not muffin, and as well as not muffin, muffin, not muffin. You get the picture. Yes, so the binomial treats them all as the same sort of thing. We want a particular order. So in this scenario, it's actually the same as what you used to much earlier on in maybe your GCSEs or your lower courses. So probability that, let's say use n, that the 5th person, the n is 5, n's the person who buys a muffin, is literally going to be 0.65, which is chance of not buying a muffin. So it's 4 of those, so it's 0.65 to the power of 4, times by this person finally buying a muffin, 0.35, which gives you 0.0625 to 3 significant figures. So it's really important you look carefully at the question. Where ordering matters, you can't use our traditional binomial formulas or books. Where order matters, look at it again from a different perspective. Think about what is actually going on there. And our final part of the problem, which should be here somewhere. There it is. Find the probability that in 20 customers, more than 15 buy tea, and, the key word there is and, at least 6 buy a muffin. So there's two parts to this question you need combining. Let's look at the probability that more than 15 buy tea. We already have this as our very first question. Okay, remember it says more than 15 buy a cup of tea. And we found the answer was 0.2375. So we'll stick to that. So x is buy tea. And the probability that x was less than 15 was 0.2375. So we only need to work out the other case. of at least 6 buying a muffin? Well, I'm going to use N or M. Let's use N because it's random. So N is a chance of buying a muffin. So N is that the event that someone buys a muffin, and there's going to be, N is a bad choice, M. N is going to be 20 customers, and the chance of them buying a muffin is, from the previous question, 0.35. We want to find out the chance that at least 6, hang on, at least 6, let me just double check with a number line. 0. Oh, hang on, we go. 1, 2, 3, 4, 5, 6, 7, 8. Well, at least 6. So at least must include 6, so 6 or more. So probability that M is greater than or equal to 6. Now, as you remember, we don't like this greater than or equal to sign. It's not in our tables, and it's a pain to work out. So let's look at the opposite case. The opposite case is the chance that M is less than or equal to 5, which is in our tables. And if you look that up, that's going to give you 1 minus 0.2454, which is 0.7546. Now, we're going to assume these two events are independent, that the chance of buying a muffin is not related to the chance of buying tea. Because that seems a bit weird, frankly. Why do you buy tea and muffins together? Must be independent. So, remember the rules of independence with probability. So, chance of getting A and B is probability of A times the probability of B. In this scenario, A was the chance of more than 15. Buying tea, and probability of B is at least 6 buying a muffin. I'm just sticking those probabilities, which gives us a chance of both those things happening is 0.17923 significant figures. So we covered 3 kind of typical style questions that just might as well come up at any time.